Hello there and welcome. Tonight we are going to travel somewhere that most maps do not show. Not because it is hidden, or because it is dangerous, or because the journey requires anything extraordinary, but because the place we are going is defined by the very thing that makes it difficult to point to, nothing. Or rather, something so close to nothing that the difference across distances of hundreds of millions of light years begins to feel philosophical rather than physical. These places have a name. Astronomers call them supervoids, and the more carefully you consider what that name actually means, the more the word begins to feel insufficient, like calling the ocean a puddle or calling a hurricane a breeze, technically accurate in its category, entirely unprepared for the scale of what it describes. We are going there tonight, all the way to the edge of the emptiest places in the universe, and then a little further still, and by the time we arrive, I think the darkness will feel different to you than it did before. I wonder where you are right now. Perhaps the room around you is quiet, the kind of quiet that only arrives when the day has finally finished with you, and you are allowed to simply exist for a while. Perhaps outside your window the sky is dark, and if you looked up you would see stars, familiar, distant, reassuring in the way that things which never change can be reassuring. What you would not see, what no human eye has ever seen directly, is what lies between those stars, between those galaxies, between the vast filaments of matter that give the universe its shape. You would not see the supervoids, but they are there, right now, as you sit in whatever warmth surrounds you. They are out there expanding slowly, silently, indifferently in the spaces where the universe has over billions of years arranged itself into the closest thing to true emptiness that nature appears to permit. If you find that questions like this one, questions that begin somewhere in the dark and end somewhere you did not expect, are the kind of questions worth spending an evening with, it would mean a great deal if you gave this video a like, subscribed. This channel is built for that particular kind of curiosity, the kind that is not in a hurry, the kind that understands that some of the most important things the universe has to show us are not the brightest or the loudest, but the quietest. Get comfortable. We have a long way to go. Let's begin. There is something the night sky does to us that is almost impossible to describe accurately. It gives us the impression of fullness, of abundance, of a universe generous with its light scattered in every direction available to anyone who thinks to look up. On a clear night far from city lights, the stars appear so numerous and so close that the darkness between them feels incidental, a backdrop, a negative space, the part of the painting that exists only to make the subject visible. That impression, as beautiful as it is one of the most profound misunderstandings available to the human eye. The universe is not full. The universe on its largest scales is almost incomprehensibly empty. The stars you see, the galaxies that astronomers have spent centuries cataloging and measuring and arguing about, are the exception. They are the rare accumulation of matter in a cosmos whose default condition is not light but darkness, not presence but absence, not structure but the vast, patient, unbroken quiet of space that contains almost nothing at all. The cosmic web, as astronomers have come to call it, is the large-scale architecture of everything. Imagine it as an enormous three-dimensional lattice, threads of matter stretching across hundreds of millions of light years, connecting at dense nodes where galaxy clusters reside, forming a structure that when mapped looks, startlingly, like the neural networks of a living brain, or the branching pattern of frost on a cold window, or the filaments inside a biological cell examined under a microscope. The universe at its largest scale looks organic. It looks deliberate. It looks like something that grew according to a plan. But look at the spaces between the threads. Those spaces, the open cells of the web, the regions where the filaments are absent, where matter long ago drifted away toward denser surroundings and left behind an expanding gulf of near-nothingness. Those spaces are where our journey is taking us tonight. They are the supervoids, and they are not small. The largest confirmed supervoid in the observable universe, a region that astronomers have been studying for 2 decades, located in the direction of the constellation Eridanus, in the southern sky, stretches across approximately 1 billion light-years. 1 billion light-years in which the density of matter falls to a fraction of what you would find anywhere else. 1 billion light-years in which galaxies exist but barely, scattered, dim, separated from their nearest neighbors by distances so vast that the word neighbor loses all meaning. To feel the weight of that number, consider where we are sitting right now. Our Sun, the star at the center of our solar system, is approximately 8 light minutes from Earth. That is to say, the light leaving its surface right now will arrive here in 8 minutes. That distance, 8 light minutes, already feels large when you try to hold it physically in the mind. The Sun is so far away that we cannot feel its heat immediately. We feel it 8 minutes after it leaves. The nearest star beyond our Sun, a small red dwarf called Proxima Centauri, is 4.2 light-years away. Not light minutes, light years. The light leaving Proxima Centauri right now will arrive at Earth in 4 years and 2 months. If you sent a message to Proxima Centauri today, using the fastest signal physics permits, you would not receive a reply for more than 8 years. The Milky Way, our entire galaxy containing hundreds of billions of stars, structured into a spiral that has been turning slowly for billions of years, is 1,000,000 light-years across. The Eridanus supervoid is 1 billion light-years across. That is 10,000 Milky Ways placed end to end. 10,000 galaxies the size of ours laid across the interior of a single region of emptiness. And inside that region, the matter is so sparse, the galaxies so few and so far between, that if you placed our entire Milky Way somewhere in the void's interior and looked out from it, the universe around you would appear thin, stretched, as though someone had taken the familiar night sky and diluted it, poured it into a container 10,000 times too large, until the light spread so thin it barely registered. But here is what the scale alone does not prepare you for. Supervoids are not simply large, they are old. They did not form recently or suddenly, or as a result of some catastrophic event. They grew the way a silence grows in a room after everyone has left slowly over billions of years, from conditions that were written into the universe in its very first moments. They are, in a sense, the oldest readable record of how the cosmos began, not written in light, but in the absence of it, not in what gathered, but in what was left behind when everything else gathered somewhere else. And they are still growing now. At this moment, as the universe continues to expand, driven by a force we have named but not understood, a pressure built into the fabric of space itself, the supervoids are becoming larger. The galaxies at their edges are drifting slowly outward, drawn toward the denser filaments that surround the voids, leaving the interior increasingly empty. The silence is deepening, the distances are growing, the threads of the cosmic web are pulling further apart, and the spaces between them are widening into something that in the far future of the universe will dwarf even what we observe today. We are living in the universe while it is still relatively young, while there is still enough structure, enough light, enough gathered matter to give the cosmos its familiar character. But the supervoids are a reminder that this character is temporary. That emptiness on the largest scales is not the exception, it is the destination. There is a particular exercise that astronomers sometimes use when they are trying to communicate scale to people who have not spent their careers thinking about it. They ask you to imagine shrinking the universe. Not all of it, just a piece of it, a manageable piece. They ask you to take something enormous and reduce it until it fits inside a space the human mind can actually hold. So let us try that now. Imagine that you could shrink the Milky Way, our entire galaxy, 1,000,000 light-years, across hundreds of billions of stars, the spiral arms, the central bulge, the vast halo of dark matter surrounding it all. Imagine you could shrink all of that down to the size of a single grain of sand. A grain of sand you could hold between your fingertip and your thumb, barely visible, light enough that you would not feel its weight. At that scale, the Andromeda Galaxy, our nearest large neighbor, the closest spiral galaxy to our own, would be another grain of sand sitting about an inch away. 2 grains of sand an inch apart. That is us and our nearest galactic companion at this scale. The local group, the small collection of galaxies that includes the Milky Way, Andromeda, and several dozen smaller companions, would fit inside a space roughly the size of a human fist. The Virgo cluster, the nearest large galaxy cluster, containing over 1,000 galaxies, would be about 50 feet away, and the Eridanus supervoid, at this scale with the Milky Way reduced to a grain of sand, would stretch approximately 6 miles in every direction. 6 miles of almost nothing. 6 miles in which our grain of sand galaxy would be lost so completely that finding it would require not just effort but an entirely different approach to the concept of searching. You would not look for it the way you look for a lost key. You would need to redefine what looking means when the object you are searching for is this small relative to the space it inhabits. That is the supervoid. That is what we are talking about when we talk about the emptiest places in the universe. But the number 1 billion light-years does not become real through a single comparison. It requires accumulation. It requires approaching the scale from multiple directions, the way you might walk around something very large to understand its shape. So let us keep walking. Light travels at 186,000 miles per second. In 1 year, light covers approximately 5.88 trillion miles. We call that distance a light year, and we use it because the alternative, writing out the actual number of miles for every cosmic distance, would fill pages before we even left our own solar system. At the speed of light, you could travel from Earth to the Moon in about 1.3 seconds, from Earth to the Sun in 8 minutes, from Earth to Pluto at the outer edge of our solar system in roughly 5.5 hours. To cross the Milky Way at the speed of light would take 1,000,000 years. To cross the Eridanus supervoid at the speed of light would take 1 billion years. 1 billion years ago, when that light would have had to begin its journey to cross the void in time to arrive at the other side today, the most complex life on Earth was single-celled. There were no fish, no forests, no insects, no dinosaurs, no mammals. The continents were arranged in shapes that would be unrecognizable to any geographer. The atmosphere was different. The oceans were different. And a photon of light, setting out from one edge of this supervoid, was beginning a journey that would not end until long after everything we consider history had come and gone. That photon is still traveling. It will be traveling for hundreds of millions of years more before it reaches the other side. And during that entire journey, it will pass through almost nothing. A galaxy here perhaps separated by tens of millions of light years from the next. Faint, small, isolated in a way that has no equivalent in any environment human beings have ever encountered or imagined. Now, here is where the picture becomes interesting in a way that the scale alone cannot capture. When most people imagine empty space, they imagine darkness, a black void featureless and uniform, extending in every direction without variation. And in a superficial sense, that image is not wrong. A supervoid is dark. It is vast. It contains very little that would be visible to any instrument we currently possess were we to position ourselves inside one. But the emptiness is not uniform. It is not featureless, and it is not in the strictest sense empty. This is one of the most important things to understand about supervoids, and one of the most counterintuitive. The universe does not permit true emptiness. Not at any scale we have yet been able to examine. Even in the most desolate regions of space, there is something. Not much, not nearly enough to matter in the way that matter usually matters, but something. Inside a supervoid, that something takes several forms. There is dark matter, the invisible non-luminous substance that makes up the majority of the universe's mass, that does not interact with light and cannot be seen directly, but whose gravitational influence shapes everything around it. Inside, a supervoid dark matter is present, but it is thin, stretched across enormous volumes like a mist so faint that detecting it requires instruments sensitive enough to measure effects that are almost too small to believe. The dark matter in a supervoid does not form the dense halos that surround galaxies in more crowded regions. It drifts diffuse and quiet, following the slow expansion of the void itself. There is also gas, primarily hydrogen, the simplest and most abundant element in the universe, the raw material from which stars are eventually built. In dense regions, this gas condenses, collapses under gravity, ignites and becomes stars. In supervoids, it does not. It remains gas. Spread so thin across such enormous distances that in a typical cubic meter of supervoid space, you might find only a handful of atoms, In the best vacuum we can create in a laboratory on Earth, a chamber pumped nearly free of all matter, there are still millions of atoms per cubic meter. The interior of a supervoid is emptier than our best laboratory vacuum by orders of magnitude. And there are occasionally galaxies. Not many, not clustered, not grouped, not connected to neighbors by the streams of gas and dark matter that link galaxies in denser environments, just isolated systems, collections of stars that managed to form in a region of the universe that did its best to prevent them. These void galaxies, as astronomers call them, tend to be smaller than average, quieter. They form stars at a slower rate because the gas available to them is limited, and the external triggers that elsewhere spark bursts of star formation, close encounters with other galaxies, streams of infalling material, the shock waves of nearby mergers simply do not arrive, often enough to matter. A void galaxy lives a long, slow, undisturbed life, and it lives that life in a neighborhood so sparse that the nearest comparable galaxy might be 50 or 100 million light-years away. To place that in human terms, if our Milky Way were a void galaxy, and we looked out from it toward our nearest neighbor at the same proportional distance, that neighbor would be so far away that the light we see from it today left before complex animal life existed on Earth. We would be looking at a galaxy as it was during the Cambrian explosion, before fish had eyes, before anything had a spine. That is how alone a void galaxy is. There is another quality to this emptiness that takes time to appreciate. It is not static. It is not a frozen thing, a region of space that formed once and has remained unchanged ever since. A supervoid is dynamic. It breathes, in a sense, slowly over timescales that make human history look like the blink of an eye. But it moves, it changes, it grows. The process by which it grows is subtle and almost paradoxical. You might expect that gravity, which pulls things together, which causes matter to accumulate, which is responsible for every star, every planet, every galaxy that has ever formed, would eventually pull matter back into the void, filling it in over time. But this is not what happens. Instead, the opposite occurs. The galaxies at the edges of a supervoid experience a gravitational tug from two directions simultaneously. From outside the void, the dense filaments and clusters of the cosmic web exert a pull, drawing those edge galaxies outward, away from the void, and toward the denser regions. From inside the void, there is almost no countervailing force. Because the void contains so little matter, the gravitational pull from its interior is too weak to compete. The result is that the galaxies at the edges drift outward, slowly, over billions of years, and as they leave, the interior of the void becomes emptier still. The void grows not by being filled, but by being vacated by the gradual departure of the matter that once defined its boundaries. It is a self-reinforcing process. The emptier the void becomes, the weaker its interior gravity, and the easier it is for remaining matter to drift away. In a universe governed by gravity, you might expect matter to always win, to always accumulate, to always fill the gaps eventually. Supervoids are evidence that this expectation is wrong. Supervoids are evidence that in certain regions, under certain conditions, the universe chooses emptiness, and having chosen it, deepens it. And having deepened it, expands it outward into the surrounding space, growing larger and quieter and more remote from everything else with every billion years that passes. They are in this sense not anomalies. They are the universe expressing one of its most fundamental tendencies, the tendency written into the very geometry of space-time by forces we are only beginning to understand, toward a future that is colder, darker, more spread out, and more empty than the present. The supervoids are not aberrations in the story of the cosmos. They are previews of it. In 1989, two astronomers named Margaret Geller and John Huchra published a map. It was not a large map by the standards of what would come later. It covered only a thin slice of the sky, a narrow wedge of the universe extending outward from Earth to a distance of roughly 650 million light-years. By cosmic standards, it was a local view, a neighborhood survey, the kind of thing you might produce if you wanted to understand the street you lived on without yet attempting to map the city. But what appeared on that map changed the way astronomers thought about the universe. When Geller and Hucre plotted the positions of the galaxies, they had catalogued more than 1,000 of them, each one a system of billions of stars, each one painstakingly measured for its distance and location they expected to see. Something roughly uniform. Galaxies scattered more or less evenly, with some clustering here and there, some regions denser than others, but nothing dramatic. Nothing that would require them to revise the fundamental picture. What they saw instead was a wall, a structure so large, so clearly defined, so unexpected in its coherence, that they named it simply the Great Wall. A sheet of galaxies stretching across the entire width of their map, 500 million light-years long, 300 million light-years wide, and only 15 million light-years thick. A flat, enormous concentration of matter, arranged as though by intention, as though some process had gathered galaxies across 500 million light-years of space and pressed them into a single plane. And surrounding the Great Wall on both sides were the voids, large, dark, almost completely empty regions where galaxies were absent, where the map showed nothing. Geller later described the pattern as looking like the surface of a sponge, or like soap bubbles pressed together, the galaxies concentrated at the places where bubbles meet, and the interiors of the bubbles almost completely empty. It was a description that captured something real about the universe's architecture, something that had been invisible until that map made it visible. The universe was not uniform, it was not random, it was structured on scales so large that no one had previously had the data to see the structure into a web. A vast, three-dimensional network of filaments and walls and clusters and voids, extending in every direction, shaping the distribution of every galaxy in the observable cosmos. That structure now has a name: the cosmic web. To understand why the cosmic web exists, why the universe organized itself into this particular pattern rather than some other, you have to go back to the beginning, not metaphorically, literally. Back to the first moments after the Big Bang, when the universe was hot and dense and almost perfectly smooth, and the word almost was doing more work than any word has ever done. In those first moments, matter was not evenly distributed. Quantum fluctuations, tiny random variations in density that arose from processes operating at scales smaller than any particle we can observe, directly created slight imbalances across the early universe. Some regions contained just a fraction of a percent more matter than average. Others contained just a fraction less, a fraction of a percent. That was all. That was the entire inheritance from which everything, every galaxy, every star, every planet, every supervoid eventually grew. A fraction of a percent difference in density written across the newborn universe by quantum chance before anything else existed. Gravity took it from there. In the regions with slightly more matter, gravity pulled harder. More matter arrived. The density increased. The gravitational pull increased with it. More matter arrived still. Over millions of years, then hundreds of millions, then billions. This process of accumulation continued slowly at first. Then, with increasing momentum, the denser regions drawing in more and more material from their surroundings. These regions would eventually become the filaments and clusters of the cosmic web. The nodes where multiple filaments intersected would become the most massive structures in the universe, superclusters, containing thousands of galaxies bound together by gravity across distances of hundreds of millions of light-years. And the regions with slightly less matter, they lost what little they had. The gravitational pull from surrounding denser areas drew their matter outward, away from them, leaving behind the expanding emptiness of the voids. The underdense regions became more underdense. The sparse areas became sparser, and the pattern that had begun as a barely perceptible ripple in the density of the early universe grew over billions of years into the cosmic web, a structure of breathtaking complexity and scale written in the language of gravity and time. Supervoids are the direct descendants of those early underdense regions. They carry within their emptiness the memory of those first quantum fluctuations. They are, in a sense, the universe's oldest readable record, not of what formed, but of what was left behind when everything else formed somewhere else. The cosmic web, when mapped in its full three-dimensional complexity, is one of the most striking structures the human mind has ever encountered. Computer simulations that recreate its formation beginning with the nearly smooth early universe and running forward through 13.8 billion years of gravitational evolution produce images that look with uncanny accuracy like photographs of actual galaxy surveys. The simulations and the observations match. The filaments appear in the same places. The clusters form at the same intersections. The voids open up in the same regions. This agreement between theory and observation is one of the most powerful confirmations in all of modern science. It tells us that our understanding of the universe's large-scale structure is not merely plausible, but correct. That the processes we have identified, gravity acting on early density fluctuations over billions of years in a universe that is simultaneously expanding, are sufficient to explain the pattern we observe. And that pattern, when you step back far enough to see it whole, is extraordinary. The filaments stretch across hundreds of millions of light-years gossamer threads of matter, so thin relative to their length that the comparison to a spider's web becomes almost inadequate. At their intersections, clusters of galaxies glow, the brightest, most active, most densely populated regions of the universe, where thousands of galaxies orbit one another in a gravitational embrace that will last for billions of years. And between the filaments, between the clusters, between the nodes and the walls and the sheets of galaxies, the voids open up, quietly, persistently, growing larger with every billion years that passes. The voids are not accidental. They are not gaps in a structure that would otherwise be complete. They are as much a part of the cosmic web as the filaments themselves. In fact, it would be more accurate to say that the cosmic web is defined by its voids as much as by its filaments, that the structure we see exists precisely because matter accumulated in some places and not in others, and that the places where it did not accumulate are just as essential to the overall pattern as the places where it did. Without the voids, there would be no filaments. Without the emptiness, there would be no structure. This is perhaps the most counterintuitive thing about the cosmic web. We tend to think of structure as something built from presence, from the accumulation of material, from things coming together and forming something coherent. But on the largest scales, structure is equally defined by absence. The cosmic web has the shape it has because matter did not go everywhere, because there were regions, vast, expanding, deepening regions where gravity's invitation was not enough, where the matter that might have gathered there instead departed for elsewhere, leaving behind the quiet architecture of the voids. The role that supervoids play within this architecture is subtle but essential. Think of it this way. The filaments of the cosmic web are rivers of matter, slow rivers moving over billions of years rather than seconds, but rivers nonetheless. Matter flows along them, drawn by gravity toward the dense clusters at their intersections. This flow has a source, and that source is the voids. As matter drains from the interior of a supervoid toward the surrounding filaments, it feeds those filaments. It contributes to the density of the nodes. It sustains the web. In this sense, supervoids are not merely the spaces between structures, they are the reservoirs from which structures are fed. They are the regions that have given up their matter, so that the filaments and clusters could grow to the sizes we observe. The emptiness of a supervoid is not simply what is left when matter leaves. It is the evidence of where that matter went and what it built when it arrived there. This relationship between the voids and the filaments, between the emptiness and the structure, is ongoing. It did not end when the cosmic web reached its current form. The web is still evolving, matter is still flowing, voids are still growing. The filaments are still accumulating the material that drains from the voids into them, and on timescales of billions of years, the pattern will continue to change. The voids growing larger, the filaments becoming denser, the clusters more massive, the web as a whole becoming more extreme in its contrasts between the full and the empty. We are observing the cosmic web at a particular moment in its evolution, a moment when it is already highly structured, when the contrast between filaments and voids is already dramatic, but when the process that created it is still very much underway. The supervoids we see today are larger than they were 5 billion years ago. They will be larger still in another 5 billion years. And the galaxies that currently drift through their interiors, isolated, quiet, forming stars slowly, in environments that provide little of the raw material, or the external stimulation that elsewhere drives vigorous galactic activity, those galaxies will find themselves over time increasingly alone. The cosmic web, patient and slow, is sorting the universe, pulling the dense regions denser, pushing the empty regions emptier, drawing matter along the filaments toward the nodes, and leaving behind in the spaces that matter has vacated the expanding quiet of the supervoids. It is not a violent process. There are no explosions, no collisions, no sudden changes. It is simply gravity doing what gravity does over the only timescales on which gravity truly expresses itself, timescales so long that the entire history of human civilization would not register as a meaningful interval. But the result accumulated over billions of years is the universe we observe, a universe of extraordinary structure and extraordinary emptiness in equal measure, a universe where the most massive concentrations of matter exist alongside the most profound absences of it, a universe shaped as much by what gathered as by what was left behind. And at the heart of what was left behind, at the center of the largest, deepest, most expansive of the voids, there is a quiet that has no equivalent anywhere else in the cosmos, a quiet we will now go deeper into. Because to understand what a supervoid truly is, it is not enough to know its size or its age or its place within the cosmic web. You have to understand where it came from. You have to go back to the very beginning of the universe itself, to a moment so early and so strange that the word moment barely applies. You have to go back to the first light. In 1964, two engineers working at Bell Telephone Laboratories in New Jersey were trying to solve a problem that had nothing to do with the origin of the universe. Arno Penzias and Robert Wilson had been assigned to work with a large horn-shaped antenna, a piece of equipment originally built to communicate with early satellites, and they were attempting to use it for radio astronomy. The antenna was sensitive, extraordinarily sensitive, and it was picking up something it should not have been picking up. A hiss, a faint, persistent, uniform hiss coming from every direction in the sky simultaneously, not from a specific star or a specific galaxy or a specific region of space, from everywhere, from all directions at once, with the same intensity, the same temperature, the same character, regardless of where the antenna was pointed. Penzias and Wilson did everything they could think of to explain it away. They checked the equipment, they recalibrated the instruments, they ruled out interference from New York City. They even climbed inside the antenna and cleaned out a nest of pigeons, along with what they diplomatically described in their notes as a white dielectric material, because they wondered if the birds were somehow responsible for the signal. The pigeons were not responsible. The hiss remained, quiet, steady, coming from everywhere, refusing to be explained by anything local or mundane. What Penzias and Wilson had discovered without knowing it, without looking for it, while trying to solve a completely different problem, was the oldest light in the universe, the faint afterglow of the Big Bang itself. A signal that had been traveling through space for 13.8 billion years, stretched by the expansion of the universe from the high-energy radiation of the early cosmos into the microwave frequencies they were detecting. A whisper from the moment the universe first became transparent to light. They called it noise. The universe was trying to tell them something, and they called it noise. It is now called the cosmic microwave background, and it is one of the most important things we have ever detected. To understand what the cosmic microwave background is and why it matters for the story of supervoids, you have to understand what the early universe looked like. In the first moments after the Big Bang, the universe was not the place we inhabit today. It was unimaginably hot, unimaginably dense, so hot in fact that matter as we know it could not exist. Protons and electrons, the building blocks of atoms, could not combine because the energy of the surrounding environment was so intense that any atom that tried to form was immediately torn apart. The universe was a plasma, a roiling, opaque sea of charged particles and radiation, all interacting constantly, all colliding and scattering and recombining in a cycle that prevented light from traveling any meaningful distance. The universe in those early moments was blind to itself. Light could not travel freely. Every photon, every particle of light was almost immediately absorbed or scattered by the charged particles surrounding it. The universe was opaque. If you had been there, you would have seen nothing because there was nothing to see. Not darkness exactly, something more like the inside of a star, so much energy in every direction that the very concept of looking somewhere and seeing something was meaningless. This continued for approximately 38,000,000 years. Then something changed. As the universe expanded, it cooled, and as it cooled, it reached a temperature at which protons and electrons could finally combine and remain combined, forming neutral hydrogen atoms for the first time. This transition, which cosmologists call recombination, happened relatively quickly on cosmic timescales, and when it happened, everything changed. Neutral atoms do not scatter light the way charged particles do. When the universe became neutral, it became transparent, and all the light that had been trapped bouncing endlessly between charged particles unable to travel freely was suddenly released. It streamed outward in every direction, filling the universe with a glow. That glow is what Penzias and Wilson detected in 1964. That is the cosmic microwave background. It is the light from the moment the universe first opened its eyes, and it contains written across the entire sky a map of what the universe looked like at that moment. A snapshot of the density variations, the slight imbalances in matter distribution that existed 38,000,000 years after the Big Bang. The tiny fluctuations that would eventually, over billions of years, grow into the cosmic web we explored in the previous chapter. When astronomers map the cosmic microwave background with precision instruments, the most detailed of which have been satellites like NASA's WMAP mission and the European Space Agency's Planck satellite, they see a sky that is almost perfectly uniform. The temperature of the background radiation varies by only about 1 part in 1,000,000 from one region of the sky to another. Tiny fluctuations, barely perceptible, even with the most sensitive instruments we have built. But those tiny fluctuations are everything. They are the seeds, the original imprints of the density variations that gravity would spend the next 13.8 billion years amplifying. The slightly warmer regions correspond to places where matter was slightly denser in the early universe regions that would eventually collapse into filaments and clusters. The slightly cooler regions correspond to places where matter was slightly less dense regions that would eventually become the voids. Every supervoid in the observable universe today traces its origin to one of those cool patches in the cosmic microwave background. Every billion light-year expanse of near-nothingness began as a fluctuation smaller than 1 part in 100 inches, the temperature of the early universe. The seed of the Eridanus supervoid, that enormous, quiet expanse we have been circling throughout this journey, was a temperature variation so small that it would have been invisible to any instrument that existed before the late 20th century. From something almost undetectable to a structure 1 billion light-years across. That is what gravity does given enough time. Now, there is a specific feature of the cosmic microwave background that brings us back to supervoids in a way that is both scientifically fascinating and genuinely strange. In 2004, astronomers examining data from NASA's WMAP satellite noticed something unusual in the map of the microwave background. In a region of the southern sky in the direction of the constellation Eridanus, there was a patch that appeared slightly colder than its surroundings. Not dramatically colder, not dramatically anything, because the entire map varies by only 1 part in 1,000,000, but colder by a measurable amount. Colder by more than the statistical models of a randomly fluctuating background would easily predict. They called it the cold spot, and it immediately became one of the most debated features in modern cosmology. The cold spot is not supposed to be there, or rather, a fluctuation of that particular size in that particular location is not impossible, but it is unlikely enough that its existence demands an explanation. The universe is not forbidden from producing unusual features through random chance, but unusual features still require investigation. They still invite the question, is this random, or is something causing it? Several explanations have been proposed. Some researchers have argued that the cold spot is simply a statistical outlier, a rare but not impossible fluctuation in the background, radiation that requires no special explanation beyond the inherent randomness of the early universe. In a sky containing as many features as the cosmic microwave background, finding one unusually large cold patch is not necessarily surprising. It is the kind of thing that can happen. But another explanation is more intriguing. In 2015, a team of astronomers led by Istvan Shapudi at the University of Hawaii announced that they had identified a large supervoid in the direction of the cold spot. Using data from surveys mapping the positions of galaxies across large areas of the sky, they found a region of unusually low density, a supervoid stretching across approximately 1.8 billion light-years located between Earth and the cold spot, roughly 3 billion light-years away. 1.8 billion light-years, larger in its mapped extent than even the Eridanus supervoid, a structure of such enormous scale that its existence alone was striking independent of any connection to the cold spot. But the connection is what made it remarkable. The connection operates through a phenomenon called the integrated Sachs-Wolf effect. It is a subtle process, and understanding it requires holding two things in mind simultaneously. First, as light from the cosmic microwave background travels across the universe, it passes through regions of varying density. When it enters a dense region, a cluster of galaxies, a massive concentration of matter, it falls into a gravitational well. It gains energy as it falls in. Then as it climbs out the other side, it loses that energy. In a static universe, these two effects would cancel out perfectly, and the light would emerge with exactly the energy it had when it entered. But the universe is not static, it is expanding. And in an expanding universe, the gravitational well that the light fell into has changed by the time the light climbs back out. The well has become shallower because the expansion of space has diluted the concentration of matter. So the light climbing out does not have to work quite as hard as it did falling in. It retains a slight excess of energy. It emerges slightly warmer. Now, reverse that process for a supervoid. When light from the cosmic microwave background passes through a supervoid, it does not fall into a gravitational well. It passes through a region of lower than average density, a gravitational hill rather than a well. As it crosses, the expansion of the universe causes that hill to become even shallower. The light that crosses a supervoid emerges with slightly less energy than it had when it entered. It emerges slightly colder. This is the integrated Sachs-Wolf effect, and it provides a mechanism by which a supervoid billions of light-years away can leave a measurable imprint on the oldest light in the universe. It explains how an enormous expanse of near-nothingness, a region defined by the absence of matter, can reach across cosmic distances and cool a patch of the background radiation by a tiny but detectable amount. If the supervoid identified by Sapudi's team is real, and the measurements suggest it is, then the cold spot may not be a mystery at all. It may simply be the shadow of an emptiness. The imprint left on the universe's oldest light by the passage of that light through 1,800,000,000 light-years of almost nothing. The void in this reading announced itself not by shining but by dimming, not by presence but by the particular quality of its absence. There is something in that idea that sits differently from other scientific explanations. Most things in astronomy reveal themselves through what they emit: the light of stars, the X-rays of hot gas, the radio waves of pulsars, the gravitational waves of merging black holes. They announce their existence. They send signals outward, and we receive those signals, and from them we reconstruct what produced them. A supervoid does the opposite. It reveals itself through what it takes away, through the slight cooling of light that passes through it, through the faint absence of galaxies in a region of sky where galaxies should be, through the behavior of light and matter at its edges, responding to a gravitational landscape shaped by what is not there. To detect a supervoid is to learn to read absence as a signal, to understand that the universe communicates not only through what it produces, but through what it withholds. That emptiness stretched across 1 billion light-years is not silence. It is a message, written in the oldest light that exists, readable only by instruments sensitive enough to detect the difference between slightly cold and slightly colder. Penzias and Wilson, cleaning pigeon droppings from their antenna in New Jersey in 1964, were hearing that message without knowing it. The hiss they could not explain was the universe speaking in the only language available to it at that distance and that age. A language not of words or signals or deliberate communication, but of temperature, of the faint warmth of creation stretched thin across 13.8 billion years, carrying within its slight variations the entire history of how the universe organized itself into what we see today. The supervoids are written in that history. They are part of the story the cosmic microwave background tells, not as anomalies or errors, but as necessary features. As the natural consequence of a universe that began with slight imperfections and spent billions of years making those imperfections dramatic. The cold spot, if the supervoid explanation is correct, is not an anomaly in the oldest light. It is a window, a place where the background radiation carries not just the memory of the early universe, but the imprint of something that formed much later, something vast and quiet and still growing, pressed gently into the ancient light as it passed through on its way to us. A billion light-year shadow cast by nothing onto the oldest thing we can see. That is what a supervoid looks like, when the universe chooses to show it to you. And having seen it, having traced the supervoid from its origins in the quantum fluctuations of the early universe, through the slow amplification of gravity to the imprint it leaves on light that has been traveling since before the Earth existed, we can now go deeper, into the interior, into the particular quality of the emptiness that waits at the center of one of these structures, into what it would actually mean to be inside one. Imagine for a moment that you could be placed somewhere, not transported there instantly, not dropped into it without warning, but placed gently, carefully, with full awareness of what was happening somewhere in the interior of a supervoid, somewhere near the center of 1 billion light-years of near-nothingness. Given a moment to look around, given time to let the environment settle into your awareness before being asked to describe what you experienced, the first thing you would notice is not what is there, it is what is not. There are no nearby stars, not dim ones, not distant ones. The stars that exist in your local galaxy, your island of matter, in this enormous sea of emptiness, are present, of course. The galaxy you inhabit still contains its hundreds of billions of suns, still glows, with its own internal light, still turns slowly on its axis, the way galaxies turn over timescales that make human history look like an intake of breath. Your local environment within your galaxy would be largely unchanged. The sun would still rise and set. The planets would still orbit. The familiar mechanics of your immediate surroundings would continue undisturbed. But look outward, look beyond your galaxy into the space surrounding it. What you would see, or rather what you would not see, is the thing that changes everything. In our sky from Earth, the night reveals itself in layers. There are the nearby stars of our own galaxy, bright and numerous, forming the band of the Milky Way. Beyond them, visible to the naked eye on a clear night, are a handful of other galaxies, the Andromeda Galaxy, the Magellanic Clouds. In the southern hemisphere, faint smudges of light that represent entire systems of billions of stars at distances of millions of light-years, and through a telescope in every direction, galaxies beyond counting, a background of distant light that extends to the edge of the observable universe, filling every patch of dark sky with the faint glow of matter that gathered billions of years ago into structures we recognize. From inside a supervoid, that background would be different, not absent. The most distant galaxies located in the dense filaments on the far side of the void would still be visible, their light having traveled across the void to reach you. But they would be fewer, more widely spaced, separated by larger apparent distances than the galaxies we see from Earth. The sky viewed through a telescope from inside a supervoid would look diluted, as though someone had taken our familiar night sky and stretched it across a canvas twice as large, so that the same number of points of light now had twice as much darkness between them. The nearest large galaxy, the closest structure, comparable to your own, might be 50 million light-years away, 100 million, perhaps more. The light you see from it left before the dinosaurs existed. Sound would not be an issue because sound does not travel through space. But even the concept of sound of vibration propagating through a medium of energy moving from one place to another through contact would feel, in the interior of a supervoid, like a concept from another kind of universe. One where things were close enough to each other for contact to occur with any regularity. One where matter was dense enough to transmit anything. Here in the heart of the void, the distances between things are so large that the very idea of transmission of one thing affecting another through proximity becomes theoretical, not impossible, just vanishingly rare and vanishingly slow. If two galaxies within a supervoid wanted to exchange matter streams of gas flowing from one to the other, the way galaxies in dense clusters exchange material during close approaches, they would need to be moving toward each other across tens of millions of light years, and the process would take hundreds of millions of years to complete. Everything that happens here happens slowly. Everything that changes here changes across timescales that no civilization has ever directly observed. This is the particular quality of the silence inside a supervoid. It is not the silence of a room after everyone has left, or the silence of a mountain at night, or even the silence of deep space between planets. It is a silence that is structural, built into the distances, a consequence not of the absence of activity but of the scale across which activity must operate in order to occur at all. Things happen inside supervoids. Stars are born and die inside the galaxies that drift through them. Planets form, chemistry occurs. Gravity operates according to the same equations it obeys everywhere else in the universe. None of the fundamental processes are suspended or altered, but the intervals between events that would connect one part of the void to another, the interactions, the influences, the moments when something in one place reaches out and changes something in another, those intervals are so vast that void's interior feels on any timescale a conscious being could experience essentially unchanged, essentially static. A supervoid does not feel like a place where things happen. It feels like a place where things simply are. What actually exists inside one of these structures, what matter is present in the interior of a supervoid, is one of the more counterintuitive aspects of the whole picture, because the answer is not nothing, not quite. Dark matter is there, thinly distributed, far less concentrated than in the filaments and clusters of the cosmic web, but present. The invisible scaffolding that makes up the majority of the universe's mass does not entirely vacate the voids. It stretches across their interiors in concentrations so dilute that detecting it requires the most sensitive instruments and the most careful statistical analysis. It does not form the dense halos around galaxies that characterize dark matter in populated regions. It simply drifts cold and invisible across the enormous volume of the void, following the slow gravitational flows that gradually draw it outward toward the surrounding filaments. There is gas, primarily hydrogen, primarily in its neutral atomic form, spread across the void's interior in concentrations that would qualify as an extraordinarily good vacuum by any earthly standard. In the emptiest regions, the particle density falls to levels so low that a cubic meter of supervoid space might contain fewer atoms than the best vacuum chambers humanity has ever constructed. The gas is there, but it does not condense into stars easily. The conditions that allow gas to collapse under its own gravity density thresholds, temperature gradients, the presence of nearby perturbations to trigger the process, are rarely met in the interior of a supervoid. The gas drifts, slowly, waiting in a sense for conditions that may never fully arrive. And there are galaxies, not many, not clustered, but present scattered through the void's interior, like the last embers of a fire that has nearly gone out. These void galaxies, as astronomers have come to call them, are among the most isolated objects in the observable universe. They exist in environments so sparse that the evolutionary pressures that shape galaxies elsewhere, mergers, interactions, the infall of fresh material from nearby structures, are almost entirely absent. A void galaxy lives quietly. It forms stars slowly limited by the gas available within its own boundaries, without the external supply that elsewhere fuels vigorous star formation. Its structure changes gradually without the dramatic reshaping that comes from collisions or close encounters. It evolves according to its own internal dynamics in an environment that provides almost no external stimulus over timescales that make even the age of the universe feel brief. If you were to observe a void galaxy carefully to study its stellar populations, its gas content, its morphology, you would find a system that looks in many respects older than its actual age. Not because time moves differently there, but because the processes that would rejuvenate it, that would trigger new rounds of star formation, introduce new material, reshape its structure, have simply not occurred often enough to keep it looking young. A void galaxy is a galaxy that has been left largely to itself, and the universe, when it leaves things largely to themselves, tends toward a kind of quiet, gradual exhaustion. There is a particular void galaxy that sits at the center of what astronomers study when they want to understand these isolated systems. Not one specific galaxy, but a type, a category of object found in the interiors of supervoids that has come to represent something almost philosophical about the nature of isolation at cosmic scales. These galaxies are typically what astronomers classify as dwarf galaxies, smaller, less massive, less luminous than systems like the Milky Way. They are found disproportionately in the interiors of voids, which makes sense given their history. Without frequent interactions with larger neighbors, without the mergers that elsewhere build galaxies into larger systems, over time void galaxies tend to remain small. They never grew the way galaxies in dense environments grew because the raw material and the interactions necessary for that growth never arrived with sufficient frequency. They are, in a very real sense, the universe's most patient objects, the ones that have been waiting the longest in the quietest possible environment for something to happen, something that may never come. Because the supervoid they inhabit is not becoming denser over time. It is not filling in. It is not gradually becoming more hospitable to the processes of galaxy formation and growth. It is expanding, growing larger, drawing the matter that remains at its edges further outward, leaving the interior increasingly empty. The void galaxies at its center are not waiting in a place that will eventually become populated. They are waiting in a place that will become progressively more isolated as time passes. They are drifting slowly toward a future in which the distances between them and any other structure are larger than they are today, in which the universe viewed from their surface contains fewer visible galaxies than it does now, in which the already sparse sky above them becomes sparser still. This is the trajectory of the interior of a supervoid, not toward complexity, not toward the kind of richness that characterizes our own environment, but toward a deepening simplicity, a deepening quiet. Now, consider what time feels like in such a place. Not in the technical sense, general relativity tells us that time passes very slightly faster in regions of lower gravitational potential, which means that clocks deep inside a supervoid would tick marginally faster than clocks in dense galaxy clusters by an amount so small as to be essentially unmeasurable without extraordinarily precise instruments. That is a real effect, and it is interesting, but it is not what I mean. What I mean is something more experiential, more about the texture of time as it would be perceived by anything capable of perceiving it. On Earth, time is marked by events, by the cycle of day and night, by seasons, by the rhythm of biological processes, by the constant occurrence of things that change the state of the world from one moment to the next. Time as we experience it is dense with events. So dense that we often feel overwhelmed by them. Too many things happening at once, too much changing, too little space between one moment and the next to simply exist without the pressure of incoming experience. Inside a supervoid, the event density collapses. Not to zero within your local galaxy. Events continue at their normal rate. Stars explode, planets cool, life, if it exists, moves through its cycles. But at the scale of the void itself, at the scale of the structure you are inhabiting, meaningful events become extraordinarily rare. A galaxy passing close enough to your own to interact, to exchange matter, to trigger any response in your local environment. This might happen once in tens or hundreds of billions of years, if it happens at all. Between such events there is simply the void, the slow expansion of space, the gradual drift of matter toward the surrounding filaments, the deepening of the silence. Time does not stop in a supervoid, but the things that make time feel full, the events, the changes, the arrivals of new information from outside those, become so rare that the intervals between them stretch into something that has no good name in human language. Something between stillness and duration. Something that is neither the frozen quality of a moment held in suspension, nor the relentless flow of time as we ordinarily experience it. Something that is simply vast. Perhaps the most unsettling thing about the interior of a supervoid is not the scale, or the isolation, or the quiet. It is the directionlessness. In most environments, space has a kind of texture, that provides orientation. There are nearby objects that define proximity and distance. There are gradients of density that indicate where more and less matter lies. There is structure, the web of filaments and clusters that provides a framework within which any given location can be understood in relation to everything else. Inside a supervoid, that framework fades. The filaments exist, but they are far away, hundreds of millions of light years in every direction past the boundaries of the void. From the interior, they are visible only as the faintest concentrations of light at the extreme edges of the observable environment. They provide no real sense of direction, no sense that one region of the void is meaningfully different from another. The interior of a supervoid is from within nearly isotropic, the same in every direction, with no strong gradients, no nearby structures to anchor the sense of orientation. You could travel for millions of light years in any direction inside a supervoid and arrive in a place that looked by any practical measure identical to where you started. The same sparse sky, the same thin distribution of dark matter, the same occasional isolated galaxy tens of millions of light years away in the direction you came from, now indistinguishable from the equally distant galaxy in the direction you are heading. In a place like that, the concept of lost becomes meaningless, not because you know where you are, but because where you are does not differ enough from anywhere else to make the distinction matter. This is the heart of the void. Not a dramatic place, not a violent place, not a place that does anything to you in the way that a black hole or a neutron star or a gamma ray burst would do something to you. Just a place where the universe has for 1 billion light years in every direction arranged itself into the closest approximation of nothing that it appears to be capable of producing. Quiet, expanding, patient beyond any measure of patience that human language was built to express. And still, despite everything, despite the emptiness, despite the isolation, despite the directionlessness and the silence and the slow deepening of the void's interior into something approaching true nothingness, still governed by the same forces that govern everything else, still expanding according to the same equations, still part of the same universe, still connected however distantly to the filaments at its edges and the clusters beyond those filaments, and the galaxies within those clusters, and the stars within those galaxies, and the planets around those stars. The void is not separate from the universe. It is the universe expressing one of its most fundamental possibilities. And that possibility, the possibility of emptiness on this scale of silence, this complete of isolation, this absolute, is not an accident or an aberration. It is, as we are about to discover, deeply connected to the force that will ultimately determine the fate of everything. In 1998, 2 independent teams of astronomers were doing something that sounds on the surface straightforward. They were measuring the brightness of exploding stars. Not just any exploding stars, a specific category of stellar explosion called a type Ia supernova, a particular kind of cosmic detonation that occurs when a dense stellar remnant called a white dwarf accumulates too much mass and undergoes a catastrophic nuclear explosion. What makes type Ia supernovae useful to astronomers is a property that borders on convenient to the point of seeming implausible. They all explode with approximately the same intrinsic brightness, every single one. Regardless of where in the universe they occur, regardless of the age of the galaxy they inhabit, regardless of almost any other variable, a type Ia supernova produces roughly the same amount of light. This makes them what cosmologists call standard candles. If you know how bright something actually is and you measure how bright it appears from where you are standing, you can calculate exactly how far away it must be. The dimmer it appears relative to its true brightness, the farther away it is. It is the same principle you use when you notice that a street light looks dimmer from a mile away than from 10 feet, except applied across billions of light years, with exploding stars instead of streetlights. Both teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other led by Brian Schmidt and Adam Rees, were using these supernovae to measure the expansion rate of the universe. The goal was to determine how quickly the universe was growing and whether that growth was slowing down over time. Gravity, after all, pulls matter together. The universe had been expanding since the Big Bang, but gravity should have been working against that expansion, decelerating it gradually. The expectation was that the supernovae would confirm this deceleration. that the universe, while still expanding, was doing so more slowly than it once had. What both teams found instead, independently using different data sets arriving at the same conclusion from different directions, was that the distant supernovae were dimmer than expected. Not brighter, dimmer. Dimmer meant farther away than the models predicted. Farther away meant the universe had expanded more than expected between when that light was emitted and when it arrived at their instruments. More expansion than expected meant the universe was not decelerating. It was accelerating. The universe was not slowing down under the influence of gravity. It was speeding up. The expansion of space was not being reined in by the gravitational pull of all the matter within it. Something else was pushing outward. Something that was not matter, not radiation, not anything that had ever been directly detected or predicted with confidence. Something that was winning against gravity on the largest scales, driving the universe to expand faster and faster with every passing billion years. They called it dark energy. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. And the thing they discovered remains more than 2 decades later, one of the least understood components of the universe. We know it exists because of what it does. We do not know what it is. Dark energy, as best as we can determine, makes up approximately 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. All of the ordinary matter, every star, every planet, every galaxy, every atom of gas and dust and rock and water and living tissue in the observable universe amounts to approximately 5% of the total. 5%. Everything we have ever seen, touched, measured, named, and thought about is a rounding error in the universe's energy budget. The overwhelming majority of what the cosmos contains is either dark matter, which we cannot see but can measure through its gravitational effects, or dark energy, which we cannot see and can measure only through its influence on the dark expansion of space. We are, in the most literal possible sense, living in a universe we do not understand. A universe whose dominant components are invisible to us, whose nature we have not determined, whose behavior we can describe mathematically, but cannot explain physically. We have given these things names: dark matter, dark energy. And in giving them names, we have created the comfortable illusion that naming a thing is the same as understanding it. It is not. But what we can say about dark energy, what the observations confirm, what the mathematics describes, is enough to understand its relationship to the supervoids. And that relationship is the key to understanding not just the supervoids themselves, but the future of the universe. Dark energy, whatever it ultimately is, behaves as a property of space itself. It is not concentrated in any particular location. It does not flow from one region to another. It is simply present uniformly everywhere, in every cubic meter of space, exerting a constant outward pressure that drives the expansion of the universe. In dense regions of the universe, in galaxy clusters, in the nodes of the cosmic web, where matter is concentrated, gravity is strong. The gravitational pull of all that accumulated matter partially counteracts the outward pressure of dark energy. The two forces compete, and in the densest regions, gravity is winning locally, holding structures together, even as the universe as a whole expands around them. The Milky Way will not be torn apart by dark energy. The local group will not be dispersed. Gravity in these dense environments is sufficient to maintain the bonds between nearby structures, even as the universe beyond them accelerates away. But in a supervoid, that competition does not occur in the same way. In a supervoid, there is very little matter, very little gravity. The inward pull that elsewhere partially balances dark energy's outward pressure is in the void's interior almost entirely absent. Dark energy does not have to compete. It operates with a freedom it does not have in dense regions, pushing space outward, driving the expansion of the void's interior, accelerating the separation of the sparse galaxies within it. This is why supervoids grow, not only because matter drains from their interiors toward the surrounding filaments under the influence of gravity, though that process is real and ongoing, but also because the space within the void is expanding more freely than the space within dense regions, driven by a dark energy that encounters almost no resistance. The void grows from within, pushed outward by the pressure of space itself at the same time as it grows from without, as matter continues to drift away from its edges. It is a double expansion. from inside and outside simultaneously. And it is self-reinforcing because as the void grows, it contains even less matter, which means even less gravitational resistance to dark energy, which means even faster expansion, which means even less matter over time. A supervoid in the presence of dark energy is a runaway system, not violent, not dramatic, but persistent, and over timescales long enough, unstoppable. Now extend this logic outward, beyond the supervoids, to the universe as a whole. The universe is currently approximately 13.8 billion years old. In that time, it has expanded from a state of extraordinary density and temperature to the vast structured, relatively cool cosmos we inhabit. The cosmic web has formed. Galaxies have gathered into clusters. Supervoids have opened up between the filaments. The universe has organized itself through billions of years of gravitational evolution into the pattern we observe. But dark energy is changing that pattern, slowly but consistently, and with a momentum that is increasing rather than decreasing. As the universe expands, the density of matter within it decreases. The same amount of matter is now spread across a larger volume of space, so the average density falls. But dark energy does not dilute with expansion, it remains constant per unit volume of space, which means that as space expands, the total amount of dark energy increases. Not because it is being created from nothing, but because there is more space, and dark energy is a property of space. This means that over time, dark energy becomes progressively more dominant relative to matter. The competition between gravity and dark energy, which today results in a universe that still has significant structure, still has dense clusters and active filaments, and galaxies undergoing vigorous evolution, will in the far future be won decisively by dark energy. And what the universe looks for, like when dark energy has won, is something that cosmologists have modeled in careful detail. It is something that the supervoids in their current state are already previewing. In approximately 2 trillion years, a span of time so large that the current age of the universe fits into it roughly 145 times, the universe will look very different from how it looks today. The galaxies beyond our local group, the hundreds of billions of galaxies currently visible in our telescopes spread across the observable universe, will have receded so far due to the accelerating expansion of space that the light they emit will no longer be able to reach us. Not because they will have moved beyond some physical barrier, but because the space between us and them will be expanding faster than light can cross it. They will not disappear from the universe. They will disappear from our universe, from the region of space that is causally connected to us, from the portion of the cosmos we can ever hope to observe or interact with. From the perspective of any observer in our local group at that distant time, the universe will appear to contain only the galaxies of the local group itself. Everything else, the Virgo cluster, the Great Wall, the filaments of the cosmic web, the supervoids, and the structures that border them will be gone. Not destroyed, just unreachable, invisible, beyond a horizon that the expansion of space has drawn around us, separating us permanently from the rest of the cosmos. The night sky in that era will be dark in a way our night sky is not. The background glow of distant galaxies, the faint light that fills every patch of dark sky, when viewed through a powerful telescope, will be absent. The universe will look from the inside of our local group the way the universe looks today from the inside of a supervoid, empty, quiet, boundless in a way that offers no reference points beyond the immediate neighborhood. The supervoids are not anomalies in the universe's structure. They are the future of the universe's structure. They are what the cosmos is moving toward, not in some regions but everywhere. Not for some observers but for all observers. The expanding emptiness that currently characterizes the largest voids will given enough time characterize the entire observable universe for every civilization that might exist within it. We are living in the brief era, brief on cosmic timescales, when the universe is still full enough to be seen, when the distant galaxies are still visible, when the cosmic web is still intact and mappable and observable in its full complexity, when a telescope pointed at any patch of dark sky will return images of galaxies too numerous to count. That era will end. Not soon by any human measure. The Sun has another 5 billion years of life remaining. The Milky Way and Andromeda will not complete their merger for another 4 billion years. On timescales relevant to human civilization, the universe is essentially static, nothing we need to plan for. But on the timescales that the supervoids inhabit, the timescales of billions and trillions of years, the direction is clear. The universe is becoming emptier, the expansion is accelerating, dark energy is winning, and the supervoids, already the emptiest places in a universe that is trending toward emptiness, are the leading edge of that future. The places where the universe's ultimate character is already most fully expressed. There is a question that this raises, a quiet, uncomfortable question that the physics does not answer, but that the physics makes unavoidable. If dark energy continues to accelerate the expansion of the universe indefinitely, and our current best models suggest it will, then the future of the cosmos is one of progressive isolation, of structures separating from one another beyond the reach of any signal or influence, of the observable universe shrinking not in physical size, but in content, of a cosmos that becomes over trillions of years a collection of isolated islands, each one unable to perceive the others, each one surrounded by an expanding emptiness that grows larger with every passing era. In that future, every region of the universe will resemble what a supervoid looks like today. The void is not the exception, the void is the preview. And perhaps the most striking thing about this realization is not what it implies for the distant future of the universe, a future so remote that no civilization we can imagine is likely to survive to witness it, but what it implies about the present, about the particular moment in cosmic history that we happen to occupy. We exist at a time when the universe is still structured, still visible in its complexity, still rich enough with nearby galaxies and active star formation and the intricate patterns of the cosmic web to give any observer within it a full and detailed picture of what the cosmos contains. We exist, in other words, at the optimal moment for understanding the universe, late enough that structures have formed and can be studied, but early enough that the expansion of space has not yet hidden them from view. In another trillion years, any civilization that exists will look out at a sky and see very little. They will have no way of knowing that the universe was once full of galaxies beyond counting. They will have no evidence of the cosmic web, no signal from the supervoids, no light from the filaments. The universe will have hidden its own history behind an expanding horizon, and the beings within it will be left with a cosmos that looks from the inside almost exactly like a supervoid looks today. Empty, quiet, bounded by nothing visible, surrounded by a darkness that extends as far as any instrument can determine without end. They will not know what they are missing. We improbably do. This is what the supervoids are ultimately pointing toward. Not just a feature of the current universe, not just a consequence of the early density fluctuations that seeded the cosmic web, but a direction, a trajectory, a slow, patient, unstoppable movement of the entire cosmos toward the condition that the supervoids already inhabit. The emptiness is not local, it is not contained, it is not a property of the voids alone. It is the universe's future written in the present tense, in the largest structures that currently exist. And knowing that, sitting with that fact, allowing it to exist alongside the warmth of wherever you are right now, alongside the light in this room and the sounds of whatever world surrounds you, changes something. Not dramatically, not in a way that demands any particular response, but quietly, in the way that genuine perspective always changes things, gently, without urgency, the way the universe itself operates, in the places where it has already become what everything else is slowly becoming. We have traveled a long way through the emptiness, through the scale and the structure and the origins and the interior and the future. There is one more place to go, one more question to sit with, not about the void, about us, about what it means to exist briefly, improbably, in a universe this vast and this empty, with the particular capacity to look outward and understand even partially what surrounds us. That is where we are going now. There is a photograph taken in 1990 that has never quite let go of the people who have seen it and understood what they were looking at. The Voyager 1 spacecraft launched in 1977, and by that point, the most distant human-made object in existence had been traveling away from Earth for 13 years. It was approaching the edge of our solar system, moving outward into the space between the stars at roughly 35000 miles per hour. On February 14th of that year, At the request of the astronomer Carl Sagan, the spacecraft turned its camera backward toward the inner solar system, toward the sun, toward home, and took a photograph. What the photograph showed was almost nothing. A vast darkness. The black of deep space crossed by scattered bands of light caused by internal reflections within the camera itself. And in one of those bands of light, barely visible, a tiny point. A pale blue dot, Sagan called it. So small that it occupied less than a single pixel of the image. So faint that it was almost lost in the photographic noise. That dot was Earth. Seen from a distance of approximately 3.7 billion miles, a distance that sounds enormous by human standards and is genuinely large relative to our solar system, but is an almost immeasurably small fraction of the distance across a supervoid. Our entire planet, with all its oceans and continents and atmospheres and cities and 7 billion people and 10,000 years of recorded history, was a pale blue dot, barely there, almost invisible. A mote of dust suspended in a sunbeam, as Sagan described it, in a darkness that extended in every direction without apparent end. Now take that image and place it within the context of everything we have explored tonight. That pale blue dot exists not in the emptiness of a supervoid, but in one of the denser regions of the cosmic web, in a spiral galaxy, orbiting a star, within a galaxy group, within a larger supercluster, within a filament of the cosmic web that connects our local structure to a vast network of matter, stretching across hundreds of millions of light years. We are, by the standards of the universe, extraordinarily well located, embedded in structure, surrounded by matter, connected through the filaments of the web to billions of other galaxies. We are not in the void, but the void is in the universe we inhabit, and understanding it, truly understanding what it is, what it contains, what it implies about the future, changes something about how the pale blue dot feels when you look at it. Consider what it took for that photograph to exist. It required a planet capable of sustaining life, a circumstance that demanded a star of the right type, at the right distance, with the right chemical composition, orbiting within a galaxy that formed at the right time in the universe's history to contain the heavy elements that rocky planets require. It required that life, once it arose on that planet, survive long enough and develop sufficient complexity to produce beings capable of curiosity. It required that those beings develop language and mathematics and the scientific method and the technology to build a spacecraft and the institutional will to launch it and the foresight to ask it to turn around and look back before it left for good. It required, in other words, billions of years of extraordinarily improbable events, each one building on the last, each one necessary for the next, stretching from the first quantum fluctuations in the density of the early universe all the way to a specific human being, Carl Sagan, standing somewhere, thinking about the fragility of things, asking a spacecraft to take a photograph that no one had asked for before. The cosmic microwave background, which we explored earlier in this journey, contains within its temperature variations the seeds of everything that followed, the slight underdensities that became the supervoids, the slight overdensities that became the filaments and clusters, and within one of those filaments, on one of those clusters, in one of those galaxies, on one of those planets, us, looking outward, measuring, thinking, asking questions about the billion light-year expanses of emptiness that exist in the universe we were born into without choosing. There is no reason from the perspective of physics that the universe should have produced anything capable of understanding it. The laws of nature do not require consciousness. They do not mandate curiosity. They did not guarantee that the particular sequence of events that led from the Big Bang to the pale blue dot would include at any point a being capable of asking why. And yet here we are, asking why. The supervoids in this context take on a meaning that their physical description alone cannot provide. They are the universe expressing its default condition, the state toward which everything is slowly moving, the vast quiet that characterizes most of what exists and will eventually characterize all of what can be observed. They are, in a sense, what the universe looks like when nothing unusual has happened, when matter has simply followed the path of least resistance, draining from the underdense regions into the filaments, leaving behind the expanding emptiness. We are what happens when something unusual occurs. When matter accumulates in sufficient density in the right conditions over sufficient time to produce stars, and around those stars planets, and on those planets chemistry, and from that chemistry life, and from that life the particular improbable flowering of awareness that looks outward at a universe mostly made of nothing and finds it beautiful rather than terrifying, that decides the billion light-year silence is worth understanding rather than simply enduring. That builds instruments sensitive enough to detect the faint cooling of ancient light caused by the passage of that light through a supervoid, and then spends years working out what that cooling means. The universe is by volume almost entirely void. The matter that exists, the stars, the galaxies, the planets, occupies a vanishingly small fraction of the total space. And the awareness that has arisen within that matter, the consciousness capable of reflecting on the void, occupies a fraction so small that expressing it as a percentage would require more decimal places than this sentence has words. We are an extraordinary improbability surrounded on all sides by an immensity that does not share our improbability. We are the exception in a universe that is mostly rule. The brief local temporary complexity in a cosmos that is trending toward simplicity. The candle in a darkness that stretches in some directions for 1 billion light years without interruption, and the candle knows it is a candle. That is the thing that the supervoids cannot do for all their scale, for all their billion light-year expanses of near-nothingness, for all their cold and silence and the slow deepening of their emptiness. They do not know they are empty. They do not experience their own vastness. They do not feel the silence. The void does not contemplate the void. We do. There is a version of this realization that feels crushing, a version in which the scale of the supervoids, the billion light-year emptiness, the trillion-year future of increasing isolation, the pale blue dot lost in the photographic noise of a spacecraft photograph, reduces everything human to insignificance, to noise, to a brief local fluctuation in a universe that will continue expanding long after every star has gone cold and every galaxy has drifted beyond every other galaxy's observable horizon. That version is available. It is internally consistent. The numbers support it. But there is another version, one that the same numbers also support if you look at them from a slightly different angle. The supervoids formed from quantum fluctuations so small that they would have been undetectable by any instrument existing before the late 20th century. 1 part in 1,000,000. A variation in density that left its fingerprint on the cosmic microwave background was amplified by gravity over 13.8 billion years and eventually produced structures 1 billion light-years across. The same process, the same initial fluctuations acting through the same gravity, over the same time also produced the filaments, the clusters, the galaxies, the stars, the planets, the chemistry, the life, the awareness. The void and the observer are products of the same cause, grown from the same seed, shaped by the same forces. The emptiness and the consciousness that contemplates it are both expressions of a universe that began as almost nothing and spent billions of years becoming something. We are not separate from the supervoids. We are their counterpart. The other thing that happens when matter is distributed unevenly across a cosmos governed by gravity and dark energy, the thing that forms in the dense regions while the voids form in the sparse one, different outcomes of the same initial conditions, different expressions of the same universe. And it is perhaps for this reason that the supervoids feel, when you sit with them long enough, less like a reminder of human insignificance and more like a reminder of human context. They are the scale against which we exist, the backdrop against which the pale blue dot appears, the billion light-year silence against which any sound, any conversation, any thought, any moment of connection between two people who happen to share a planet on the edge of a spiral galaxy in the outer arm of a filament of the cosmic web becomes, by contrast, something worth noticing, worth protecting even. We began tonight with a place defined by absence, by the near-total emptiness of one of the largest structures in the observable universe, by the billion light-year silence of a supervoid expanding slowly in the space between the threads of the cosmic web, growing larger with every passing billion years, containing within its vast interior almost nothing, a few sparse galaxies, a thin haze of dark matter, the faint whisper of ancient radiation passing through on its way to somewhere else. We traced its origins to the first moments of the universe, to quantum fluctuations smaller than 1 part in 1,000,000 preserved in the cosmic microwave background, amplified by gravity across billions of years into the structures we observe today. We found its shadow in the cold spot, pressed gently into the oldest light in existence by the passage of that light through a billion light-years of near-nothingness. We stood in its interior and felt the particular quality of a silence that is not the absence of sound, but the consequence of distances so large that the very concept of proximity becomes difficult to apply. We watched it grow, driven by dark energy, operating in a region where gravity offers almost no resistance, and we followed that growth outward into the future, to a universe that will eventually resemble, for every observer within it, the Proking Beta de Blevo, interior of the supervoid we have been exploring tonight. A universe of progressive isolation, of receding horizons, of an expanding emptiness that will ultimately separate every structure from every other, leaving each one alone in a darkness it cannot see past. And then we came back to the pale blue dot, back to the improbable accumulation of matter and time and chemistry and life that produced on the surface of a small planet in the outer arm of a spiral galaxy, beings capable of asking what lies in the spaces between the galaxies. Beings who built instruments sensitive enough to detect the cold shadow of a supervoid on light that has been traveling for 13.8 billion years. Beings who looked at 1 billion light-years of almost nothing and found it worth understanding. That capacity, the capacity to look outward and comprehend, even partially, what surrounds us, is not guaranteed by the laws of physics. It is not written into the equations of general relativity or the standard model of particle physics. It arose against enormous odds from the particular conditions of one small planet in one unremarkable galaxy, in one of the denser regions of a universe that is mostly void. It is temporary. Everything about it is temporary. The sun will eventually exhaust its fuel. The Earth will eventually be consumed. The Milky Way will eventually merge with Andromeda, and the resulting galaxy will eventually exhaust its star-forming gas, and its last stars will eventually cool to darkness, and the darkness will persist for longer than any number expressible in ordinary language, before even that darkness is changed by the slow processes that operate on timescales the universe has not yet reached. Everything is temporary, but temporary does not mean unimportant. It does not mean unreal. It does not mean that what occurs within the temporary interval is without weight or significance or beauty. The supervoid does not know it is empty. The billion light-year silence does not experience itself as silence. The cold shadow pressed into the cosmic microwave background carries no awareness of what it is or where it came from or what it means. We carry that awareness, briefly, improbably, in this narrow window of cosmic time when the universe is still structured enough to be seen and understood and wondered at. On this small planet, in this unremarkable galaxy, in this dense, lucky corner of a cosmos that is mostly void. The warmth in this room, whatever warmth surrounds you right now, whatever light is nearby, whatever sounds drift in from the world outside, is not the default condition of the universe. It is the exception. And the exception, as the supervoids remind us when we look at them long enough, is the most extraordinary thing the universe has managed to produce. It is here now, in this moment, on this world, a single point of light and warmth and awareness, floating in a darkness that stretches in some directions for 1 billion light-years without interruption. And from somewhere in that darkness, from some isolated galaxy drifting through the interior of a supervoid, if anything were there to look, that point of light would not be visible at all, but it is here. And for now, that is everything.